Okay, welcome to the second talk of this parallel session, where we have a presentation about sort of quantum communication over bosonic Gaussian channels, which is given from Kyungjoo from AWS. Please go ahead.
Right. Thank you so much. Thank you so much for the kind introduction, and thank you everyone for coming to my talk. So today I'm going to present the work that I did when I was at Yale in collaboration with Stefano Pirandola and Liang. So I'm going to talk about the quantum capacity of Gaussian thermal loss channels, and in particular, I'm gonna present how a multi-channel strategy may be more advantageous than single-channel strategies. So yeah, here's the setup that I want to consider. So I want to consider a setup where we have an information sender, Alice, who has this input state, and she sends this input state through some noisy channel, which may be corrupted by some energy attenuation. And then the receiver Bob is going to receive some noisy output state, and this noisy output state is generally going to be different from the input state that Alice sent in the first place. So the question that I want to address in this setting is like how many qubits can be faithfully transmitted through this noisy channel. So here, by faithfully, I mean with essentially 100% fidelity. And this question is equivalent to asking what's the quantum capacity of this noisy channel? I mean, this is the definition of the quantum capacity. So to get a sense of what quantum capacities are, like I like to give some obvious examples with some obvious answers. Excuse me. So first, when we have some ideal qubit channels, the quantum capacity of those ideal qubit channels is going to be precisely 1, because we can just use this channel to send 1 qubit with 100% fidelity every single time we use this ideal qubit channel. On the other hand, when we have noisy qubit channels, we can send 1 qubit, but that qubit is going to be corrupted by some noise. So because of that, it doesn't qualify the faithfulness condition. And to make faithful transmission, like we need to apply some techniques like quantum error correction or entanglement distillation. And those techniques always come with some overhead. So at the end of the day, on average, we can only send strictly less than 1 qubit per channel use when we have these noisy qubit channels. And lastly, when we have ideal bosonic channels, the quantum capacity of that channel is going to be infinity, and this is simply because the bosonic modes are infinite dimensional. So when that channel is noiseless, we can then just send infinitely many states or infinitely many qubits. So now, to be more specific, for the purpose of this talk, I'm going to focus on the lossy bosonic channels. And what I mean by that is I'm going to imagine a scenario where the channel is surrounded by some environment, which is in a thermal state. And moreover, I'm going to assume that the input state interacts with the environment through this beam splitter interaction. So as a result, only some fraction of this input state makes it to the receiver side, and the other fraction is lost to the environment. And this lost state is not going to be available to Alice and Bob anymore. And an important parameter here is the transmissivity of the beam splitter or the loss probability of the beam splitter. So when we have unit transmissivity, for instance, we have perfect transmission or lossless transmission. And on the other hand, when we have vanishing transmissivity, we have complete loss of information. And another important parameter is this n-thermal, which quantifies the average thermal photon number in the environment. So when that state is a vacuum state, then we say this channel is a pure loss channel. And when that state has a non-zero average thermal photon number, we say that this channel is a thermal loss channel. And lastly, we impose an energy constraint on this input state. So in other words, we only want to consider some input states that have maximum n bar photons on average. So with this channel being introduced, I'm going to present some known results about this bosonic channels to just give some sense of what the quantum capacities are like for these channels. So for pure loss channels, where we have vacuum in the environment, and also in the energy unconstrained scenario, which means like we now allow these input states have some infinitely many photons. In such a setting, like the quantum capacity of this pure loss channel is known to be given by this formula. And in the case where we have some unit transmissivity, this expression diverges, and this is as expected. I mean, this with unit transmissivity, this is an ideal bosonic channel, so its quantum capacity has to be infinity. On the other hand, if the transmissivity is less than or equal to 0.5 or 50%, we can see that the quantum capacity vanishes. And I'm not going to dive deeper into this, but this is consistent with the quantum no cloning theorem. So this was for the energy unconstrained case. And now, like, if we look at the energy constrained case, where we now like restrict the maximum average photon number in the input state, then we have this slightly different expression. And now, like, even if we have this unit transmissivity, the quantum capacity of this pure loss channel is given by this G function like Gn bar, and this is finite. And this Gn bar is simply the entropy of a thermal state with an average photon number n bar. And again, like on the other hand, when the transmissivity is less than or equal to 50%, we again have vanishing capacity, and this is consistent with the no cloning theorem. So in this talk, like so a lot of things are known about the pure loss channel where we have vacuum state in the environment. So in this talk, the problem that we want to focus on is what's the quantum capacity of a thermal loss channel where we have some non-zero thermal photon number. And in particular, we are going to focus on the energy constrained cases where the input state can only have some finite energy. And our result is that there is some non-trivial multi-channel strategy which outperforms the best-known single-channel strategy. And therefore, we established the tightest lower bound of the quantum capacity of thermal loss channel known to date. So to go deeper into the quantum capacity, I'm going to introduce the concept of coherent information. So coherent information of a channel with respect to some state rho is defined by this formula. S here is the von Neumann entropy, and NC here is the complementary channel. So the precise definition of the coherent information doesn't quite matter for the purpose of this talk. What matters for now is that this is some purely entropic quantity, meaning like these are based on some entropies. And operationally, this coherent information quantifies the maximum attainable entanglement via the entanglement distillation, using this channel and using this input state. And in particular, we can define this quantity called regularized coherent information. And here we are maximizing the coherent information over many channel uses, here like n channel uses, and over that collective state rho. And the result of this optimization, and which is divided by the number of channel uses, is called regularized coherent information. And this is a highly non-trivial result, but this is shown to equal this purely entropic quantity is shown to equal the quantum capacity of the channel. And because of the need for doing this regularization, taking n to the infinity, it's generally really hard to compute the quantum capacity of a generic channel. But like on the other hand, for some special class of channels, namely degradable channels, it's known that only taking n equals 1 is sufficient. And it's therefore much easier to compute the quantum capacity for such channels. And pure loss channels are such an example. And this was exactly the reason why a lot of our pure loss channels were already known. So to briefly give an overview of where we are today, like we know that for pure loss channels, inputting a single mode thermal state, when we are under some energy constraint, inputting the single mode thermal state is known to be the optimal strategy, and this is a single channel strategy. And similarly, in the energy unconstrained case, we can just simply input an infinite temperature thermal state, and again, this is known to be an optimal strategy, even including multi-channel strategies. Now, on the other hand, for thermal loss channels, our result is that there's this multi-mode correlated thermostat, which provides some non-trivial multi-channel strategy that outperforms the best known single channel strategy, namely using single mode thermostat. But our technique does not provide any improvement in the energy unconstrained case. So the single mode thermostat still remains to be the best known strategy. And I'll go into more detail later in the later part of this talk. So before diving deeper into bosonic channels, I'm going to introduce some simple example that basically inspired my line of thought. So for that purpose, I'm going to consider this simple qubit depolarization channel, which leaves the state with the probability 1 minus p and replaces the state by some maximally mixed state with some probability p. And in this case, it is known that the best single qubit strategy is to input this maximally mixed state. And there's an alternative strategy, which is using a 5-qubit input state. This input state here is kind of like using a 5-qubit repetition code. So this plot is taken from a textbook by Mark Wild. What's shown here is that, most of the time, this single channel strategy with maximally mixed state outperforms this 5-qubit strategy. And this is simply because, in this 5-qubit strategy, only 1 qubit is transmitted using 5 channels. So even if we are in the noiseless case, we only send 1 qubit per 5 channels. And because of that, in the most parameter regime, like 5-qubit channel strategy is outperformed. But if we really zoom into this highly noisy regime, then we can see that there is some noise parameters where the 5-channel strategy outperforms the best single channel strategy. And in other words, this is saying that this qubit depolarization channel is the quantum capacity of this qubit depolarization channel is super additive, meaning there is some non-trivial multi-channel strategy that outperforms the best single channel strategy. And this super additivity is a unique feature of quantum information theory, which is not present in the classical information theory. So now, what I did at the time was I basically wanted to look at this example in the language of bosonic states and bosonic channels. So the way I decided to look at this single qubit state is I wanted to look at it as an infinite temperature single qubit thermostat. And analogously, the way I wanted to look at this was I wanted to look at this as a thermostat that has some correlation, namely when one of the bits is 0, all the other bits have to be 0, and the same goes for 1. So this was the kind of language that I wanted to use when I was looking at this example. And with that, I'll take this inspiration to bosonic channels and dive deeper into the bosonic problem. So coming back to this single mode thermostat, we have discussed that the single mode thermostat is the optimal input state for pure loss channels, which are degradable. Now for thermal loss channels, we know that this is the optimal input state among Gaussian states and among single mode states. And even in the single mode case, it's not yet known whether this Gaussian thermal state is an optimal state. So in principle, it's possible that there may be some single mode non-Gaussian state that might outperform this single mode thermal state. Now our result is that we present some multi-mode Gaussian state that outperforms this single mode thermal state when we have thermal loss channels and when we are under this energy constraint. So by correlated multi-mode thermostat, we mean this specific construction. So our construction is that initially we prepare many single mode thermostates which may have some different photon numbers, and this initial energy imbalance is going to be uniformly distributed through this Gaussian Fourier transformation, which is basically mixing the annihilation operators of all of these modes through a discrete Fourier transformation. So in the end, we are left with some correlated multi-mode thermostat, which where each mode has exactly the same average photon number. But now, these different modes may be correlated with each other. because of this initial energy imbalance. And a simple example of this correlated multimode thermal state is constructed in the following way. So we can think of like this very dramatic way of imposing an energy imbalance. So we can consider like inputting all the energy in the first mode and set all the other modes to be in the vacuum state. So this initial energy imbalance can be redistributed through this Fourier transformation. And in the end, like every mode has n bar photons on average. So to dive deeper into this state, like we can consider its covariance matrix. And I2 here is simply a 2x2 identity matrix. And we have 2 here because we have, in each mode, we have position and momentum operators. And along the diagonal elements, we can see that there's this n bar contribution. And this simply means that each mode here has n bar photons on average. And now what's really interesting is that in the off diagonal elements, we have this non-trivial component like n bar times identity. And this demonstrates that all of these modes are correlated with each other. All the quadrature operators are correlated with each other. So with this, I'm going to present the main result. So again, like to remind everyone, we are considering the thermal loss channel where we have non-zero average thermal photon number, and we are going to consider the energy constrained scenario. So now, like in this energy constrained scenario, the single mode strategy is to use this single mode thermal state, and our multi-channel strategy is to put in the first x times n modes this highly energetic thermal state, and for the rest of like 1 minus x n modes, we put the vacuum state. And again, these are distributed through Gaussian Fourier transformation. So first, like our numerical result shows that like when the loss probability of that thermal loss channel is pretty high, then there's those regimes where the multi-mode thermal state outperforms the single mode thermal state. And on the right-hand side, we are showing the optimal mixture of the thermal state with the vacuum state. So over here, we have this, we have this unit mixture saying that 100% of the time we are using a thermal state and we are not using a vacuum state here. And as we go from here to here, we begin to mix some more vacuum states. And this curve shows the optimal ratio between a thermal state and the vacuum state. So again, like this shows that the correlated multi-mode thermal states can outperform the single mode thermal state. And now, like to gain some more understanding of why this advantage happens, like we are going to focus on the specific loss parameter, which is 19%. And in this 19% loss probability case, it turns out that the optimal strategy is to use a thermal state with this larger photon number, roughly 41% of the time, and use the vacuum state, roughly 59% of the time. And I'm going to explain where these numbers are naturally coming from. So to do that, like here, like we are now focusing on this specific loss parameter. And now we are plotting the achievable rate as a function of the allowed average input photon number. So as we allow more and more energy, we can send more information. But the way this curve grows is really interesting. So initially, it has this convex behavior, and eventually it has this concave behavior. And because of this initial convex behavior, there's this non-trivial boundary that is like above this blue curve. And if we look at where the non-trivial interception happens, it's happening exactly at this 2.458 photons. And that basically explains why this 41 and 59 mixture is the optimal strategy when we are only allowed to use 1 photons on average. So this, so what this means is that this initial convexity makes it possible that there may be some non-trivial advantage coming from taking this this non-trivial boundary, and where the non-trivial boundary is determines like what's the optimal mixture between a thermal state and a vacuum state. So an interesting remark is that for degradable channels, it's known that the coherent information that we are plotting here is always concave, And in that case, this boundary is always the same as the blue curve, and there's not going to be any advantage in using such a multi-mode thermostat. And the second point is that, you know, the curve is eventually concave. So in this specific parameter, like after like we reach this specific photon number, there's no advantage in using a correlated multi-mode thermostat. So eventually in the energy unconstrained case, our scheme does not provide any non-trivial advantage. So to recap, like we have, so in the energy constrained case, we have shown that the multi-mode correlated thermostat can outperform the single mode thermostat. But unfortunately, in the energy unconstrained case, the non-trivial advantage disappears, and the single mode thermostat is the best known input state so far. And lastly, I want to briefly remark that, you know, this mixing two strategy idea can also be useful for two-way communication settings. So in the previous setting, we were mixing a thermostat with the vacuum state. And here we are analogously mixing two different strategies. And here we're mixing like forward and backward strategies. And I'm not going to dive deeper into these you know, details. You can check the details in the paper, but this mix and match idea was also shown to be quite advantageous. So with that, I'm going to briefly summarize what we were up to. So we introduced this correlated multi-mode thermostat. We showed that it can sometimes outperform the single mode thermostat. And we explained this behavior based on this convexity of the coherent information. And also, you know, in our paper, we have also discussed some extensions of this idea to two-way communication setting as well as private communication setting. So for those of you who are interested, please check out the paper. And also kind of going forward, I think an interesting question would be like whether this simple and general explanation might apply to some other, you know, interesting settings. So that could be an interesting question. And also, like everything we have considered so far is Gaussian. I mean, this multi-mode thermostat is a Gaussian state. So another important question might be like whether there's some non-trivial advantage coming from using a non-Gaussian state. And I think it's still a largely unexplored area. So lastly, I want to point out that this work was done in collaboration with Stefano Pirandola and Liang Jiang. And with that, I want to thank you everyone for the attention, and I'll take some questions if there's any.
Cool, thanks a lot for this interesting talk. So there are two questions so far. Ming Yu is asking whether it is possible to build such correlated thermal states in another input channel. And by another input channel, I think he thinks that the input channel should be considered as some noise.
Mm-hmm. So let me see. So the question is whether this correlated thermostat can also be advantageous for other channels than the thermal loss channel. Would that be?
I think so, yes.
Yeah. So there was an earlier paper, which is mentioned in our paper, where they showed some different type of correlation, maybe advantageous for some lossy channels, but that lossy channel is a little bit different from this specific loss channel. So in that other setting, the environment has a thermostat, but that environment also had some mutual correlation. So this was a little bit different setting. In that different setting where the environment is correlated, it was also shown that some correlation in the input state may help. So okay. This is pointed out in the paper.
I have a comment about this distinction between a channel being degradable and then sort of the capacity is easy because we don't need the regularization, and if it's not degradable, then it's hard. So I remember sort of QIP 2 years ago or something like this, where Felix Leditsky, Graham, and Debbie, they made use of the continuity of the quantum capacity to sort of approximate the capacity of channels which are not degradable, but they are sort of close to degradable. Suppose in your setting, suppose you would have a thermal noise channel where this parameter nth would be very small. Then one could sort of expect by simply continuity arguments that that sort of the standard thing that works in the pure loss channel is still a good, I mean, the codes, they are still good codes, for example. Did you think about this? Or this could be also be used maybe to benchmark the results you have, how good they are in a setting where this nth is small.
Right, so yeah, I mean, I have thought about it, and actually a lot of people have worked into some similar ideas. So there were some papers where they basically represented this thermal loss channel using a pure loss channel plus amplification. And in the case where this n thermal is really, really small, the amplification is close to being identity. And we can kind of understand this channel in terms of pure loss channel, which is, you know, well known. And based on that, we can establish an upper bound of the quantum capacity of the thermal loss channels. And those, you know, upper bounds are currently close to being the best upper bound known so far. But unfortunately, you know, when we compare this lower bound with the upper bounds are still like way up here. So it's not gonna be even be visible in this scale. So it could be that these upper bounds are not yet tight enough, or it could be that we can do better on the lower bound side, but there's still a large gap between the two, and you know, reducing that would be an interesting, you know, question. So yeah, thank you for the question.
So maybe we end this talk with two questions that I tried to merge by Marius Junge and Earl Campbell, that sort of are both asking, if I understand it correctly, something similar. And they are sort of asking whether the improvement that you observe in the unrestricted case, whether this is observed or whether this is a proven statement. Whether the optimal.
That there is no.
Yeah, sorry.
Right. So at least, you know, it's proven that using our specific strategy, like we don't see any advantage in the energy unconstrained case. I mean, we have thoroughly optimized to make sure that it doesn't happen, but it doesn't mean that there's some better, clever strategy that might really outperform the single mode thermostat. So that's still a huge open question, whether in the energy unconstrained case, whether there's some better state than this infinite temperature thermostat.
Very good. Thanks a lot again for answering all the questions and the talk.
Yeah, thanks so much.
Thanks.